Correlation and regression are perhaps the most frequently used statistical techniques in the social sciences. Both are concerned with the relationship between two or more variables that are measured on an interval ratio scale. Correlation is the simpler of the two, so we'll start our discussion with that. This chart shows the relationship between the median age at which women marry and the median age at which men marry for a sample of respondents to the General Social Survey. It's an extremely useful chart analytically since it provides anyone looking at it with lots of information. You probably remember charts like this from high school algebra. Each point represents a couple and the age of the man and the age of the woman when they got married. For this couple here, for example, it looks like the man was about 26 and a half and the woman was about 25. Overall, the points are fairly close together and the relationship is a positive one. As the age for women increases, the age for men also increases. There's some variability in the data, but overall it looks as if women marry men who are just about a year or so older than they are. This point over here is a little bit of an outlier, but not by much. The woman in this couple married a man who is about 3 years older than she was. By the way, this chart is called a scatter plot or a scattergram. Here's another one. This one shows the relationship between births per woman and literacy rate for a range of countries. It's quite a bit different from the previous scatter plot. First of all, the relationship depicted here is negative or inverse. As literacy rates increase, births per woman decrease. This phenomenon, by the way, is called the demographic transformation. These countries up here, for example, have very low literacy rates and very high birth rates. These down here have high literacy rates, but low birth rates. Unlike the other chart, however, the points here are more spread out. For example, looking at this group over here, countries at about the 50% literacy rate, you can see that some have relatively low birth rates, whereas others still have high birth rates. Even down here, looking at countries with nearly a 100% literacy rate, there's still a good deal of diversity among birth rates. Let's take a look at another one. This chart shows the relationship between age and marathon run times in hours. It's hard to see any kind of relationship in these data. There are young runners with slow times, moderate times, and fast times, and older runners also with slow, moderate, and fast times. A scatter plot like this one suggests that there's no relationship between age and marathon speed. Here's another one showing the relationship between residents' median income and tax revenue. Pictures like these provide a first step in getting an idea of the relationship between the two variables. With them, we get a general sense. The closer the points are clustered together, the stronger the relationship, etc. That said, there are a lot of points to contend with. It can be difficult to get an accurate view of what's going on. That's where the correlation coefficient R comes in. R gives us a number that describes the relationship between these variables mathematically. Here are some facts about R. R ranges from -1 to +1. Strong correlations are close to -1 or +1, and weak ones are close to 0. Negative values indicate an inverse or negative correlation, and positive values indicate a positive correlation. Here R equals 0.72, indicating a fairly strong relationship between height and weight. The sign of R is positive, which means that the relationship is positive. As height increases, weight increases. Here R is 0.19, indicating a weak but positive relationship. There are several methods for computing R, and I think this one has the benefit of being fairly easy to calculate, while at the same time providing an explanation of how the formula works. Essentially, the numerator in this formula provides an indicator of how x and y vary together. Recall first how you calculate a z-score. You subtract the mean of the values from each value and divide by the standard deviation of all the values. If a z-score is positive, that means that the raw score is above the mean. If it's negative, then the raw score is below the mean. If both z-scores are negative and we multiply them together, we get a positive number. If both are positive, when we multiply them together, we also get a positive number. When we sum these numbers up, the number we get will be larger if there are fewer instances when the z-scores have different signs. And as the formula here shows, the larger the numerator, the higher the value of r. As usual, it's best to organize the summation with a summation table. And here's a summation table for you, showing how to calculate r. This shows you the relationship between education and the number of hours the respondent spends on the internet each week. I was actually a little surprised by this. The correlation is quite high, as you can see here on the bottom right-hand corner. Here's another example. Each dot represents a neighborhood's property crime rate and the median home price. In this scatter plot, it's very hard to see whether there is a correlation. If there is one, whether it's positive or negative. We need to know r for this, and a value of 0.48 indicates a moderate correlation. Now, suppose I'm a real estate investor interested in buying properties that I can rent out. Wouldn't it be useful to be able to estimate property values based on a single variable like crime rate? As the correlation coefficient shows, there's at least a moderate relationship between these two. To predict property values given crime rate, we need to compute what's called a regression line. A regression line gives us the change in the y value based on a 1-unit change in the x value. I've computed it here along with another value called r squared, which we'll get into shortly. What this equation says is that for every 1-unit increase in property crime rate, there'll be a $4,285 decrease in property values. Just a note, I've expressed the property values here in hundreds rather than hundreds of thousands, so therefore we have to multiply the coefficient shown on the screen by 1,000. That's how I get the 4,285. 428,000 is the y-intercept, the point at which the regression line crosses the y-axis. And if you extend the line with your eye, you get an idea that that's about right. Microsoft Excel never draws these with perfect accuracy, but it looks to me as if that line would cross around 440 or something like that. The general formula for the regression line is y equals b times x plus a, where b is the slope of the line and a is the intercept. The point where the line crosses the y-axis. The formula for b, if you look at it closely, is really not all that different than the formula for the correlation coefficient, at least with regards to the numerator. As with r, we get that numerator by computing a covariance, which is essentially a statistic that describes how x and y vary together, and then we divide that by a statistic that describes how x varies by itself. The formula for the intercept here is self-explanatory. But what really is a regression line? In a nutshell, the regression line is the single line that can be drawn through these points that maximizes the sum of the distances from each point to itself. Because of the way it's calculated, we call it the least squares regression line. I've drawn these distances here in orange to show what I'm talking about. In this case, only one of the points actually touches the line, our red regression line. But nonetheless, this is the only line that minimizes the sum of all these orange lines. Just for fun, I'll draw another line. Even though this line intersects 3 of the points, the increase in the distances between the remaining points is larger than the decrease that occurred because the other points now touch the red regression line. There's just one more thing to introduce on this slide, and that's this thing over here called r squared. R squared is called the coefficient of determination, and it's literally Pearson's R squared. R squared gives us the percentage of variability in the relationship between x and y that's explained by y. In this case, it tells us that 23% of the variability in property values is related to property crime. Well, what explains the other 77%? Well, it could be many things. It could be the size of the homes, it could be the quality of the schools, it could be access to public transportation. There's nothing in this model that gives us that. These are only guesses. To explore that question, we need to perform a multiple regression analysis. In multiple regression, we can have as many independent variables as we need. Each will have its own slope coefficient, and if we choose our independent variables correctly, we ought to be able to get an increase in the value of R squared, indicating greater explanatory power of our model. We don't cover multiple regression in a course like this. It's a huge field, and you could easily take 1 or 2 graduate level courses only on that subject. Let's just take a look at one more bivariate relationship. This scatter plot shows the relationship between the number of runs scored and the number of runs prevented. That's the runs differential value along the horizontal axis. And the number of wins for selected Major League Baseball teams in, I think it was 2015. Just to be sure you understand the chart, negative values for runs differential indicates that the team allowed the opposing team to score more runs than it scored itself throughout the course of a season. Positive values indicate that the team scored more runs than it allowed the other team to score. Not surprisingly, the greater the value of the runs differential, the more wins the team had. We can calculate the number of runs for a given runs differential value by multiplying the value that you see in the equation, the B value of 0.1014, and adding 80.969, the intercept. Let's look at the R squared value, though. It's about 0.86, indicating that the runs differential explains about 86% of the variation in wins. Notice that the points here are clustered very closely to the regression line. And think back and compare it to the R-square value for our property crimes property values chart. You step back in the video, you'll see that our points were quite a bit further away from the regression line, and that at the same time we also had a much, much lower value for R-squared. As I said before, regression is a huge topic in statistics and one of the most powerful tools used by social researchers. With regression, in particular multiple regression, we can hold several independent variables constant and see whether and how a variable of interest affects a dependent variable. Again, we've barely scratched the surface when it comes to our discussion of regression. I do hope, however, that there's enough material here to help you understand the literature that you're going to encounter as you go forward in this field.